Hello, everyone. As the presenter just said, this is about 4-axis machining in Inventor CAM. Basically, the same thing I'm going to show you today will pretty much work with the SolidWorks HSM. It will also work with Fusion 360. So the technology is basically the same throughout the products that Autodesk has. I happen to be using Inventor CAM today, so we worded it that way. But it does work with pretty much any of the Inventor CAM products. Now, the topic is 4-axis machining. But you'll notice as I go through my presentation today, I'm going to be talking quite a bit about part modeling. Most of the success you're going to have with machining in a 4-axis mode, a lot of it really depends on what the model has in it and how the model is displayed. So I'm going to be showing you both modeling techniques and machining techniques to get some of your weird 4-axis stuff rolling. I just noticed a couple attendees dropped off. Hopefully they're not having web problems. But anyway, the first thing I'm going to show you is technically not 4-axis, but I just want to talk about having your models actually match what you're machining, or have your machining actually match what you expect in the model. Because sometimes what you draw as a model and what you machine is going to end up being different. I feel it's important that you guys recognize the differences and go from there. So again, the first one, not exactly 4-axis, but we will get there. So let me do this. I'm going to bring this model up on the screen. I do keep my model simple because it's all about concept, but at the same time, I want you to fully understand the step-by-steps that I do to create things. I was going to create all this live for you, but I realized I wouldn't have time in 1 hour. So a lot of what I'm going to show you today is pre-created, but we're going to walk through step-by-step as to how it was created. Okay, just an example, this first part. If I drag the end of the part up, you'll notice it's basically just a cylindrical extrusion. It is 4 inches diameter and it's 1 inch thick. So those numbers may be important a little bit later, but anyway, it's a 4 inch diameter disc. I put a few work planes in here. We're going to be doing a little bit of slicing and dicing visually with those work planes. But ultimately, what I wanted to focus on is the slot. I have a slot in here that has a sloped bottom on it. This tends to be a little sticky issue for some people, so let's take a look at this a little bit closer. The first thing I did is created one sketch. Let me just show you a quick look at that sketch. All it is just one single line that runs from the center of the part out to the edge of the part, and I've positioned it a 1/2 inch off the top. All I'm doing with that line is basically establishing a 1/2 inch depth. In addition to that sketch, I've got another sketch, which is 90 degrees from the first one. Same basic principle, it's just a simple line, but it establishes a 1/4 inch depth. So I'm going to have a 1/2 inch deep on one side, a 1/4 inch deep on the other side. So those are two sketches I put in there just to start with. Now I do have another sketch here. Let me edit that real quick. What this line represents is the slope that's going to occur from the 1/2 inch depth to the 1/4 inch depth. Now this number here, this is basically a formula. Since I have a disc that's 4 inches wide that's got a 2 inch radius, this is basically 2 times 2 times pi divided by 4. Now, just to kind of explain the math, basically radius times radius squared. So you've heard the pi r squared is the circumference of a circle. That's exactly what I've done. It's pi r squared, but I divided it by 4 because I only want this to go 1/4 of the way around that disc. So it's going to go around that disc exactly 90 degrees. So it's pi r squared to get the total circumference divided by 4 because I only want to go 1/4 of the way around. Now what I did with that sketch is I actually created a 3D sketch out of it. Now this sketch, let me just kind of make that sketch visible there. That one. We'll make it visible so you can see it. The 3D sketch, all that is, edit sketch. I use this tool right here to project a curve onto a surface. So all I did is projected that line onto that circular face. And you can see that line basically creates a new 3D sketch that goes 1/4 of the way around that cylinder. So that's how I established all my goods. Now, what did I do with all that? Basically, I made this surface. So let me just hide some of these sketches here real quick. I'll leave that one visible. I'll hide this one. Okay, so what I did is I created this surface. Now, what that surface is, I took that bottom line, it's a sweep. My first profile curve is this bottom line right here. So I'm sweeping that straight line up the path curve, which is this outside 3D curve I was just showing you. So I'm taking this line and I'm sending it up that slope. Now I drew the other line in there just for reference to show I'm actually not using it with my sweep. So I basically have one line sweeping up another line. I am using this guide orientation and I'm telling it to follow this circular surface. That's the outside surface of the cylinder. So basically as it goes around, it's twisting as it goes up, which creates the surface you see highlighted on the screen. So with all that being said, the last sketch I made is just a slot. I have two things in here. I have a line representing the center of the slot, and I've got the slot drawn itself. So all I did is said, let's just make an extrusion of that slot that goes to that selected surface. So what do you end up with? You end up with a circular slot with a sloped bottom. Okay, again, not exactly 4-axis, but we're getting there. All this is kind of important. You'll see a little bit later on. So that is the way most people would model a typical slot in a part. You establish where the bottom is. You just draw your slot and you say extrude to the bottom. Boom, done. Or maybe extrude and find some way to create the bottom. Either way, it's got a sloped bottom. Now, for machining on that, how do you machine something like that? Well, most people, they would jump over to the machining side. Switch over to CAM here real quick. Let me generate that toolpath. What they will do is they will use that centered line and do what's referred to as a trace operation. The trace operation is basically go into the part, follow the line, and come out. So here's my trace operation. If I do a quick simulate on that, you can pretty much see that it just goes into the stock, makes the cut, and comes out. But here's a question for the group. Is that cut I'm creating going to actually match the model? Well, if you're using a flat 1/2-inch end mill like I am, the answer is no, it's not going to match the model. Okay, so let me give you an example here. Let me go back to the modeling side. The way I modeled this, anywhere I slice this model, if I slice it at 30 degrees, do a half section view here. If I look right at that plane, you'll notice my slot is perfectly squared, which represents, you know, a perfectly square end mill that you're putting in there. So if I slice it at 30 degrees, again, you'll notice it's perfectly squared. If I slice it at 45 degrees, again, perfectly square. If I slice it at 60 degrees, again, perfectly square. No matter where you slice it, there's a perfect little square slot because I designed that surface to be flat no matter where it's sliced. But if you machine that, that's not what you're going to get. So exactly what are you going to get? Well, let me just go back to the CAM here, do a quick simulate. We'll turn on the stock so you can actually see it. I'll go ahead and run this. It should run fairly quick. We're just going to dive in. We're going to walk right up that slope. And we're going to come out. Now, because I have a flat end mill, you might notice a little oddity going on down here in the corner. Half of that tool did not cut all the way to the slope, did it? Okay, a lot of people think they drew the slope. That's exactly what the model showed. How come it didn't machine that? Well, it's real simple. The bottom of your tool is flat. It's not sloped. So you're always going to get a little bit of a flat at the bottom. And this one doesn't show it quite so much, but you could have a little bit of flat up at the top. Actually, since the tool was dragging up that slope, the top of it is actually sloped. But you'll notice you do have a little flat down here at the bottom. So maybe it's important for you guys to make sure that the model matches what the machined part is actually going to be. Now, there's other ways to machine this part. I could get a smaller ball cutter and go down there and whittle it to death. But most people are going to want to use the big tool and just cut it quick. So if you're worried about interferences with maybe a pin that might go down into that slot or some other mechanism, sometimes you may want to model the part the way it's actually going to look after it's machined. So let's take a quick look at that. Okay. I have another part I'm going to open up. So I'm going to show you a little bit different approach here. Now, what I did on this particular part, I've got the same extrusion, I've got the same work planes. Actually, I just copied the other part to make it easy. I've got the same sketches. There's the one line, there's the other line, there's the flat slope line. I've got the same 3D sketch in here. Everything is identical except this extrusion. Last time when I made that extrusion, I selected the entire slot and just told it to cut that slot out. This time, I'm ignoring the slot. I'm just grabbing a 1/2 inch diameter circle on the end. See the 1/4 inch radius right there? So I'm going to use that. And this time, the only thing I'm really doing different is I'm telling it to make a new solid rather than cut the existing solid. So when you pull the trigger on this, what you actually end up with is one solid body that represents the part, another solid body that's going to represent, let's say, a 1/2 inch diameter tool. I actually labeled it as tool. So if you think about this, I have that sketch, which is basically the center line of that slot projected down onto that surface. So you'll see the center line of that slot right there is flat. I projected it onto the bottom surface, which has given me a center line that's sloped. Very easy to do, guys, very easy. So what I'm going to do here is in your modeling side, I can say I want to sweep using a solid. The default here is using geometry. Hit this little button right here. You can say I want to use a solid. They call this a tool body, like a 1/2 inch end mill. So I can grab that tool body, tell it to follow a given curve, like the one I've got drawn in the bottom of that, if I can find it. There it is. And as I'm doing that, I can tell it to cut. What am I cutting? I'm cutting the other solid. So I want to cut that solid. There's a little preview of what I'm going to get. Now you'll notice you have in the preview a little bit of flat here at the bottom. You have the slope. And you'll notice you also have a little bit of flat up here at the top. Because that's how the tool is going to, basically you're emulating, you're pretending that this red solid is going to be the tool making the cut. So it's a different way of making the slot. So if I come in here and take a look, you can see the little flat on the bottom. You can see the slope. And if I start slicing it, you think about this. I go to work plane, go to view. Let's do a 1/2 section view like I did before. Let me get to the default isometric view. Let's do a 1/2 section there. There we go. One thing you'll notice difference, I'm slicing it at 30 degrees. Remember last time I had that perfectly flat bottom? Well, if you take a round tool and you drag it up a slope, the bottom's not going to be perfectly flat. It's going to have a little bit of that curvature of the tool in it. I think you can see that curvature right there. So right there it shows curvature. If I slice it at the 45-degree work plane, you can see the same curvature. If I slice it at the 60-degree work plane, you can see the same curvature. Now, if I sliced it down on the very end, which I don't have a plane there, I wish I did. Again, you would notice down here at the bottom, when the tool initially plunges in, it is flat down there. So there is a way to model exactly the way it's going to look when it comes off the machine. That's one of the things I wanted to show you today, and this becomes kind of important when you start getting into rotary work. Because the way you design a slot versus the way the machine might actually cut it can look two entirely different ways. That's the part that I wanted to show you. I don't know if I have CAM on this one. Yes, I do. So let me just go back over to CAM, generate the toolpath. Again, you're not going to see anything different this time other than when I simulate this and play it. If I do an actual show part comparison, you'll notice that the part and the cut are pretty much 100% identical now. There's no mismatch between the part and what was actually cut. Before, there was a little bit of mismatch. So that's the first thing I wanted to show you is how can we make our parts match our machining or vice versa? All right, the next thing I want to show you, let's go in here, take a look at the next category, pockets on the side of a part. There's two things I wanted to pretty much show you here. The first thing is, what if you have a normal square pocket on the side of a round part? Now, that's good. You know, I do have a flat pocket in here. But the first thing you need to learn when it comes to machining in different orientations, especially wrapping and things like that, is how do you get your tool to align? You notice my setup is set up for lathe. I've got my setup here. I've got Z pointing down the center of the cylinder, which is the way you would chuck this up on a lathe. I think most of us would agree with that. You put the Z on the front of the part, that's your turn cylinder. Now, when you have a flat pocket on the top, your tool has to come down vertically. So you notice my Z has changed here. If I'm looking at my setup, my Z is pointing out the side. If I go to this flat pocket, my Z is pointing up. Well, obviously to machine the top of this, I need to have the tool coming from up above. Okay, so how do you do that? Well, it's real simple. If I edit this toolpath, there's only one thing you really have to do. You select your tool. I got a 1/2-inch flat end mill. On the second page, there is a tool orientation. All I had to do is select the Z-axis plane and an X-axis. My Z-axis plane is basically the surface you see there highlighted. My X-axis, I just picked the edge of that pocket. So that basically sets up your X and Z in this orientation. So now the tool is going to come down from the top. Without that, your tool is going to be trying to come in from the side. And it can't even see the pocket from this Z direction. So you really need, let me undo that. You really need your tool to come down in a different orientation. Now, I showed you the tool in here to make that happen. What this does, it's actually going to send out a rotation code to your machine to get from the front of this part to the top of that part. Since it's rotating on the X-axis, you should get a 90-degree X rotary or an A-axis rotary. A usually aligns with X, B with Y, C with Z. So you would get a 90-degree A-axis rotation. Assuming your machine can rotate in that direction, that's what you're going to get on an output. So this is going to trigger your A, B, or C rotation code. As far as that goes, the rest of it's plain Jane. You know, if I simulate that, yeah, it's just a pocket. So I hit play, turn that off so it'll run a little bit smoother. And voila, pocket. Okay, now, in addition to that, I have another type of slot here. I've got a wrapped slot. Now, how do you draw a wrapped pocket? One simple way to do it, and there are some implications here, is to start with a sketch. Now, in my case, I started with this sketch right here. If you look at the numbers at it, it's basically located 4 inches off the end of the cylinder. It's a 1-inch wide slot, and you might recognize that number. Basically, what that number is, since we've already discussed it, that is the circumference of this cylinder, which is pi r squared. The circumference of this cylinder divided by 4, because I only wanted my slot to go across 90-degree spread. So if I did some dimensioning on that wall there, I don't know if I could do this on inspection or not. Let me see if I can touch that line and maybe that line, see if it'll give me an angle. Yeah, right there, angle 90 degrees. So basically, to get a 90-degree slot, I have to consider the circumference of the cylinder divided by whatever angle I want, 90 out of 360, which is 1/4. Okay, so again, you take that, and all you have to do is do an emboss command. Now, the emboss command, if you've never done it before, is actually pretty simple. You click your profile, which is my rectangle. You can see it highlighted there. You put in your depth that you want to go. Now, you can do this as a raised embossment or as a cut engraving. I'm doing mine as a cut. I'm telling it to go 1/4 inch deep. And you tell it wrap to face. Now, when you turn on wrap to face, you select the face that you'd like to wrap it around. So by doing that, I end up with this wrapped pocket. Now, there's some good and bad to that. I just wanted to show you how I actually created the wrap pocket. Okay, now when you get ready to machine something that's been wrapped, you go back over to the CAM side. We'll generate these toolpaths. Okay, you've got the wrap pocket there. Now, with this machining operation, there's basically 2 things you need to do. First of all, we'll just do a quick edit on this. The tool, I'm using the exact same 1/2 inch end mill, not a big deal. But right here on the second tab, notice it says Wrap Toolpath. When you wrap a toolpath, you basically pick your cylinder. I'll clear that so you can see this. You pick the outside of the part. That's going to be the wrap cylinder. Now, you notice it shows a wrap radius of 2 inches here. The 4-inch disc has a 2-inch radius. Now, if I tell it to wrap the cylinder based on the bottom of the pocket, notice my wrap radius is a 1/4 inch difference. So now it's looking at a 1 3/8 or 1 3/4 radius versus a 2-inch radius. So you can use either one, but there is a gotcha, and I'm going to show you this in just a second. So you can use the bottom of the pocket as your wrap radius, or you can use the outer cylinder as your wrap radius. I'm going to leave it on the outer cylinder. That's really all I did is wrapping the toolpath. By the way, let me uncheck that. Notice the tool orientation is here, just like I showed you a minute ago. If you don't use tool orientation like I did on this first pocket, you know, keep in mind on the first pocket, I wanted the tool to come straight down. Well, this pocket, your tool actually needs to be rotating. So we are getting into rotary machining now. So you don't really give a tool orientation because you can't have your tool coming straight down from the top. It has to rotate with the cylinder. So instead of using tool orientation, I just tell it to wrap it. So again, just 1-click difference. Pick your cylinder, it shows you what radius you've selected. There is an offset here, we'll talk about that in a second. So now the tool is actually going to be following the curvature of the cylinder, i.e. 4th axis machining. Now, there are 3 commands that have this built into it. What we call wrap toolpath, there's 3 commands. That is the 2D adaptive, the 2D pocket, and the 2D contour. A lot of these other milling operations do not have wrap options yet. Right now, it's only in these 3. It's been in these 3 for a while. There is a beta version out that actually has it in other places, but I don't demo beta. I don't show anything until it's done, released in the product. I don't like pointing people to futures. This is what we have today. It is in adaptive, pocketing, and contouring. Well, of course, I'm doing a pocket right now. So your end result toolpath is a pocket mill that wraps to that cylinder. Okay? If I do a quick simulation on this, hit play here, you can see it walk around, and it cuts out a rotary pocket. I'm going to make a slight change here. Let me rewind that. I'm going to show the stock is transparent. I'm going to hit play again. Again, I've just got it plunging. By the way, you probably do this in multiple depths. I'm doing everything today simple, one tool pass, so you can see it. Obviously, in real life, I'd probably take multiple passes going down just because I've got a lot of material here. Just pretend it's a really soft plastic. But notice here, as I watch this come around, actually, let me just get rid of the holder for a second so you can see the actual tool. As this is coming around, this is going to be the final pass. There's something I want to show you here that's a little bit peculiar. Again, a lot of this demo is to show you the gotchas about 4-axis machining, as opposed to just throwing some part up there and say, hey, this is how you do it. I do a lot of phone support, and I deal with calls coming in all the time, and people struggle with the same things over and over and over again. So I chose to show some of those struggle points. Notice right here, the tool is basically walking right down that edge. Zero clearance, perfect cut. Now, when I get down here to the end wall, it's a perfect cut right along that edge. If I go up the other side, it's a perfect cut. Let it get finished here. Of course, with that great big tool, I'm going to have radiuses in the corners, as to be expected. I could use smaller tools. I chose not to. But if I get this done, and I say, show me the part comparison, notice I've got an issue. And by the way, this is one of the support calls I get. Hey, I just did this slot, and it's cutting the heck out of the end of my part here. See those big orange patches? It cut into that wall. See that undercut? We can't have that in real life. You can't have undercuts. So you got to ask yourself, why all of a sudden is there an undercut there? Something's not right, okay? Well, let me show you what is actually going on in real life. We'll close the simulation. That wrapped pocket, let me go back to the modeling. I'm going to edit this sketch here. I actually have a little tool drawn up in here that this is your 1/2-inch end mill. I have a rectangle here. It's exactly a 1/2 inch wide. And I'm going to show you when you wrap a tool, that tool is actually using the same center as your part is. Anytime you wrap a pocket or tell a tool to wrap around a cylinder, guess what? They're all using the exact same center point. Now, what that happens with this tool, we used a wrap radius equal to the outside diameter of the part. So what's happening is the tool, let me move this tool. I've got this set up to where I can swing it back and forth to show you like the motion of the tool. If this tool is going back and forth, sorry for my jumpy graphics. Okay, if my tool is going back and forth like this, okay, when it comes over to the top, if you told it to use the wrap radius on the outside of the cylinder, that tool is going to stop right there, where you're at the outside of the cylinder. Okay, that's as close as I can get it by hand. Notice what's happening to the bottom of the tool. It's actually gouging that wall. Why? Because the slot is a perfectly 90-degree slot based on that center point. Your tool is using the same center point, but you've got this difference. Now, if I pulled the center line of the tool on over to the edge of that slot, you notice you'd have a perfect alignment. But guess what? We don't cut with the center of the tool. We actually cut with the side of the tool, right? So if you're cutting based on the outside diameter, there, you're going to be undercutting by that much on that sidewall. Okay? So that's why. Now, if you tell it to cut based on the lower inside diameter, like right there, you would be undercutting here and not gouging at the bottom. So you need to decide, are we going to use the outer cylinder as the limit control, or are we going to be using the inner cylinder as the limit control? Okay, and that is the one option you have in that wrap toolpath command. Let me go back to machining here real quick. Okay, now last time I showed you, let me just do the setup and generate the toolpaths. Okay, that wrap pocket, last time I was showing you that we were using the full 2-inch wrap radius. So I chose the outside of the cylinder. This time I'm going to clear that. I'm going to choose the bottom of the pocket as my wrapping cylinder. So I'm showing a wrap radius of 1.75 this time. When I say OK, there's my new toolpath. If I simulate that, just fire this off real quick. I'll try to slow it down when it gets to the last lap. Come on, get down here. Okay, when it comes into this last lap, again, it's never a problem on the sidewalls because that 1 inch never changes. But when I come down here, because I'm using the bottom of the pocket now, it's not going to gouge that sidewall, but notice it's leaving a little bit of distance here at the top of the tool. Now the bottom's actually on the corner. I don't know if I can rotate the screen careful enough to show that. The bottom is truly getting into the bottom, but notice at the top, you've got some uncut area here. So no matter how you approach this, as long as the tool and the part are sharing the same centerline axis, you're going to get one variation or the other. Now, I will tell you guys, I feel like, and I thought about this, I feel like I'm pointing out all the bad parts of the software. My point is, I want you guys to be educated, and I want you guys to understand why things are working the way they are working. And by the way, me personally, I've worked with EdgeCam, SmartCam, CamX Command, SDRC. I have been through 9 or 10 different machining softwares. I have a pretty broad knowledge of what the other guys are capable of doing. And by the way, they all use the same math algorithms for this type of procedure. So it doesn't matter whether you're using our product or someone else's product, you're going to be fighting the same battles because they're all using the same math. Okay? Just to point that out, it's not a flaw in the software. I'm just showing you how we can get around that flaw. Okay? So you can see there's a little bit of a mismatch there. Again, all that depends on whether you tell that wrap pocket to use the 1 3/4 radius or the 2-inch radius. Or by the way, if you grab one of these, you can offset that. Let's say I offset it by 1/8 of an inch. I can actually split the difference. That's why they give you an offset value here. So I can actually tell it to go halfway between the bottom of the pocket and the top of the pocket. So if you don't want to completely overcut or you don't want to completely undercut, you can split the difference. And it'll actually split the difference and do half and half. But again, because I'm showing you all this, of course, I have a possible workaround. I've actually provided this to a few people on phone support as a workaround for this type of machining. How about if we start lying to the software? There's a concept for you. How do you lie to the software? Okay, of course, we all do it, right? What I did is I made a sketch. Let me slice the graphics, come in here. I said, what if I compensate for that 1/2-inch tool? So I took this wall and I offset it 1/4 inch. I took this wall and I offset it 1/4 inch. That is where the center line of the tool resides. I think we all agree on that. Simple math. Now, if I extend those two center lines down, they actually meet at this point right here. So I extended them down, created a point, and then I drew a circle on that point. Now, why did I do that? Real simple. Because Inventor can do multi-body solids, I made an extrusion based on that center point. That extrusion is using that sketch. I basically made a solid. I think it goes all the way through the part. It didn't have to. Or maybe it just goes an inch deep. I don't remember. But I made an extrusion there, but I made it as a second solid. Okay, that's food for thought. So let's go back to the CAM side. My first setup is using the center of the part. And you saw the two tool paths that I created, that one and that one, right? I made a second setup, but on my second setup, I didn't mean to double click that. On my second setup, come on, show it to me. I actually used the center of that little cylinder. So I'm making a setup based on that is my pivot point. Everybody's scratching their head saying, oh, yeah, that will probably work. Duh, why didn't I think of that? Okay. So I made a second cylinder. I set up a setup based on that. Of course, it throws your stock off a little bit. Honestly, I don't care how big the stock looks as long as it cuts what I want it to cut. Okay. So I made a second setup and I did another wrap on that same pocket. Let me generate that real quick. So there it is. It pretty much looks identical to what we had before. But again, look at the center that I based everything on. So now if I simulate that one and do a quick play on this, it goes in, does its cutting. Of course, again, more stock showing, but I don't care about that. As it cuts all this, oh, that was the last path, wasn't it? Okay. See if I can zoom in on this. Run it forwards. You'll notice as it comes down to that sidewall, right there, it's actually doing a perfect cut on that sidewall, top and bottom. Kind of hard to see that the top and bottom are following that. Maybe I can get to it at a 45-degree angle. So there it is. You can see that I'm basically hugging that wall with the top and the bottom of the cutter. So it's now a perfect cut on that sidewall. If I could get your guys' applause, that'd be great. But no, we have another problem that just showed up. If I go ahead and simulate this on out, yes, we got perfect cuts on the sidewalls. But what happens when you offset your rotational center up like I did? You might notice the sidewall back here. Let me do a show part comparison. If you look at that, because I've got an elevated center, I have an elevated crown in my part back there. Yeah, come on. Trying to rotate the screen and show you this. But see how it's elevated in the center? You can see the arch right there. And you can see the arch on the other side right there. Yeah, we got the perfect cut on this end wall, but we did not get a perfect cut on that side. Why? Because we have an elevated center, which elevates your wrapping radius, which basically gives you your crown and your whole pocket tool path. So even though I gave you a workaround to get perfect sidewalls, now we've got a secondary issue to deal with. But believe it or not, I do have a total solution for you. If you do the wrap pocket on the original surface, and if you do a wrap pocket on the fake center, then you actually took both of them and ran them, you would end up with the first one being cut, which is going to machine the bottom of the pocket. Then you're going to end up with the sidewalls being cut. And what you end up with there is a perfect cut on all four sides. No gouging, no overcuts, no undercuts. Everything is cut clean. So hopefully that makes sense to you guys. If I run them both, and by the way, the second run didn't even have to be a pocket mill. It could have just been a one-pass contour. But since I had the pocket mills already drawn up, I figured I'd show it that way. So that is some cute little tricks on plain radial 4-axis pocketing. I am going to get a little bit deeper. Every step goes a little bit deeper. So with that being said, let's take a look at the next example. Let me open this up. Open up side slot B. Actually, side slot A. So some people have to do cams and slot work on the sides of cylinders. I see this as a common failure when I see people do slots. Again, this sketch is fairly simple. It's a 1/2 inch wide, so a 1/2 inch tool. You recognize that number. That's basically telling it from center to center. I want to go 90 degrees around the cylinder. We're going 1.5 inches up. We're going to go 3 inches, and we should have 1.5 inches on the backside. So it's basically just a typical slot. Now, the number one thing that I see people do with a slot like this is they will go to their modeling and they'll do an emboss. Okay, so if I go to emboss, you basically pick the profile that already saw it. You could join or cut. I do want to wrap to face. So I'm going to wrap it to that face. You can kind of see the little red preview there. Looks like exactly what I want. So when I say okay, voila, perfect little slot. And it's exactly 90 degrees. It's got the dimensions on it I want. So it's going to go in 1 inch. It's going to transition and go out 1 inch. So again, perfect little slot, fairly easy to come up with. But guess what? It's not right. Again, I'm trying to show you what you're going to encounter in real life. This slot is not what you think it is. If I take that embossment and go a little deeper with it, let's say 1/4 inch, can anybody see anything wrong with it? Actually, if you look carefully, you'll notice there's a little bit of taper going on with it. The embossing, when it wraps around the cylinder, I've got that perfect 1/2 inch at the outside of the cylinder. But the closer it gets to the center, that size is actually reducing. Check this out. If I edit that feature and go 1 inch deep, you can tell that that embossment is reducing all the way through that slot. You see the V-notch in the front, you see the V-notch in the back, and you can actually see it here if you compare the width of that to the width of the top. So that's something that people run into, and actually if you go all the way down, and I can prove the math here, 1.999, I can't go all the way to 2 inches because it'll fail, but if I bring it all the way to the center, everything in that slot basically points to the center line of the part. So it's at the center line of the part here, all the way through that, it's at the center line of the part. So if you followed the bottom of that groove, you basically have a straight center line. That's what the emboss command does. I just wanted you guys to be aware of that. Okay, now, how do you get around that? Well, this obviously is not working. So we'll throw that away. I'm going to open up slot B and show you a different approach. This is the same approach that I did just a minute ago on that other part. If I go to create a sweep using solids, I can use this as my 1/2-inch tool. I want to align that with the outside cylinder. Basically, it's going to use that center line. I want to select this solid as the one that I'm cutting. I do want to do a cut. And the curve I want to follow is this curve. Now, rather than wrapping the entire slot, all I did is I wrapped the center line. That is a 3D sketch tool. I'll back up and show it to you in a second. But notice the end result. It's going to use that tool body to actually cut that slot out. And you're going to end up with a slot that looks exactly like it would if it came off the CNC machine. You'll see some radiuses in here as it's going down that slope. That is basically exactly what you'd have coming off the machine. So again, it's one of those things. Do you want to have the model look exactly like the machine part? This method will do it. Now, I told you I'd go back and show you that 3D sketch. There's the 3D sketch. Basically, all I did was I used this project a surface. I grabbed that black line and told it to project it to the cylinder. And that's where that purple sketch came from. So it's not a complicated thing to do. So that is one approach. Now, you'll notice to machine something like this. On the machining side, let me just actually open up another part. On the machining side, what happens is you create a toolpath. Now, ideally, let me zoom in on this. Ideally, what you would want to do on the machining is you'd want to take that blue line, which pretty much follows the center line of that slot. I think you can see it go through there and come out. So you would want that as a path, and then you just want to trace it, right? Well, actually, when I was prepping for this demo, I tried doing the trace on it. And guess what? If you try a trace, there is no wrap option. I told you earlier, the wrap option is only in adaptive machining, pocket milling, and contouring. Unfortunately, the trace, it's not in there yet. So I was like, okay, if I can't trace the center line, how am I going to machine this silly thing? Well, real simple. What I did, and again, you guys can do the same thing, is I just did a regular 2D contour. And with that contour, let me show you what I actually selected. I'm going to edit that. Same 1/2-inch tool I've been using all day. Right here, I am wrapping the toolpath. My wrap cylinder is the 2-inch radius. It's the outside of the cylinder. For a contour, all I had to do is select one side of that pocket. Since that pocket is perfectly drawn and it's a 1/2 inch all the way through, I don't really need to know where the center is. I can use the edge of the pocket. So I basically said, I want to contour that line. I've got it highlighted in red right now. You can see that is my contour selection shown in blue. So basically, I'm just saying, okay, follow that contour. Now, if you follow the contour and you're telling it to wrap, your toolpath is going to show up here at the top of the part. Okay? To compensate for that, you know, if you think about contour, most of your compensation is stepping sideways. I want to step down. So what I did to compensate for that is I basically just went to my depths page, my heights page. I said, take that selected contour and just go down another 1/2 inch. So basically, I'm just telling it to push that toolpath down a 1/2 inch from where it is. And that's how the toolpath ends up at the bottom center of that slot. So with that being said, again, just a quick simulation on it. Just hit play. You can see it just walks right through there. So long story short, guys, this tool is basically doing the exact same thing as my tool body is doing when I created the slot in the first place. So it's 100% perfect match. So that looks exactly like the model. If I actually show a part comparison, it should come up and really show no differences whatsoever. Yeah, it's hard to rotate the screen without messing that up. So, okay, one last thing to show you. I've got about 8 minutes left. There is a simple stuff, what I call simple. These slots and stuff I'm showing you is probably the most difficult thing you could do in 4-axis. But just an example, to do a slot like this, maybe you've got a thread or a screw or something that just needs to keep going. You know, the last one I showed you, a side approach, slope, and then going out. This one's, you know, what if you have this? Well, the way I created this is real simple. I started with one sketch, extruded the cylinder. I made another sketch. Now, the purpose of this sketch, because I wanted my cut to go out of the part on both ends, I drew a line from center to center, and then I just added a 1-inch extension on each end. All that 1 inch is for is just to make sure I go 1 inch beyond the solid itself. Okay, so that's all I did there. I went into 3D Sketch. By the way, if you go into 3D Sketch, they do have a helical curve option. Under my 3D Sketch is my helical curve. All I did on that is I told it the diameter of my cylinder, which we knew it was 4 inches. I wanted a 2-inch pitch, and I wanted to make 4 revolutions. Now my part is 6 inches long, but since I extended it 1 inch on each end, I actually have 8 inches of total length. So 4-inch diameter, 2-inch pitch, 4 revolutions adds up to 8 inches. And then I basically just anchored this top point on that point right there just to tell it to start at the perfect 90-degree point. So that's how I created that. Once I had that path in there, let me just make it visible. I told it I wanted a work plane at the end of that path normal to the path. Now, if you notice, it is slightly tipped. You want your plane to be normal to that path. You don't want it flat, because if it's a 1/2 inch wide, and you're going through as a spiral, your groove is going to be less than a 1/2 inch. So make sure your tool is lined up with that path. Now, all I did there is I created a sketch. There's my helical sketch. Here's my other sketch. That sketch is basically my 1/2 inch wide tool, 1 inch because I wanted to go a 1/2 inch deep, and I've got it sticking out a 1/2 inch. I usually just center it and tell it how wide and how long. So there's the tool path, and then I just did a sweep, and I told it to do a cut. So that's how my slot ended up in there. I think that's self-explanatory enough. From there, I did come in here to machining. Let me just generate the tool paths here. The first time I attempted to cut that, I basically told it that I wanted to do a pocket mill, because I knew pocket mill would clear out the whole pocket. I was going to use an undersized cutter, 3/8 of an inch. But when I pocket milled it, I realized it would not run out the end of the part. I needed my tool to actually go beyond the edge of that surface. If you just say pocket that, your tool center stays inside that outline. So my tool center was about where my cursor is, and I had corners here that weren't being cut. I thought, okay, well, I can solve that. So I just did a contour on one side of the slot. That's the contour for the left side of the slot, as I'm going to call it. Okay. Then I did another contour for the right side of it. So basically, I've got 2 contours, one walking through right to left, the other walking through left to right. Now, there's nothing special in these that I haven't already showed you. Just going to go to Edit, Tool, I use a 3/8 tool instead of a 1/2 inch. I am wrapping the tool path based on my 2-inch diameter, 2-inch radius. No special depth considerations. I did have to turn off all my lead ins and lead outs. I did not want all those arcs in and arcs out, and I just basically wanted to do a plunge. But I did put a 2-inch extension on my lead in. Now, where does that show up? Right here. If you see that green arc right there, my wall ended right there where my cursor is. But I wanted the tool to keep going. So I basically just told it to do a 2-inch extension. It does follow that same contour. So now you can see the blue is where the toolpath actually ends. This green is basically just the lead out. I did the same thing on the lead in. I really didn't have to have it on the lead in, but I did it anyway, just to show you that 2-inch extension does follow the contour. So with that being said, I can grab this setup, say simulate. For the bird's eye view here, we'll just run this. You can see it kind of goes through. It's cutting, looks like the side that's closest to me. Again, if you have a really deep pocket, you want to do this at multiple levels. I'm just doing a single level. I found when I do multiple levels, you get so much geometry going on in there, it's really hard to explain things and let people see what they need to see. Then I come back in and I basically climb cut the other way to machine the other side wall. So completely exiting the part on both ends, I'm getting a nice clean cut in and out. Let's go ahead and finish that out. Again, you can rotate the part and look at it and see that everything's pretty much nice clean cuts, perfect match. So I guess the only thing I haven't shown you is post-processing. In my case, I'm going to my posts. I do have like a mill turn setup. This can actually be 4-axis milling or mill turn. I'm just going to post it as a mill turn. I've got a Haas machine. If I post it, hit save. Yeah, it's already there. It comes up, and you can obviously see got everything turning the machine on and getting it oriented. And you see a series of Z with the C-axis move. There's your rotation. So it's moving the Z, which is the length of the part, putting your C-axis rotation moves in, and between the two, you get the perfect spiral cut. So again, an hour is not a lot of time to show you everything that's possible with 4-axis. My main purpose today was showing you that 4-axis machining may or may not actually match the 4-axis parts that somebody gives you. Because when you're dealing with flat-ended tools, you do get some interesting results and mismatches. Hopefully I've shown you enough to be able to handle situations like that when you run into it. Again, in my opinion, machining is one half of the process. How you build the model is the other half. They do need to coincide with each other. But there's usually a way to get a perfect 4-axis toolpath, even if you have limitations in the software. And again, I hate pointing out our limitations, but by the way, it's a limitation in all the softwares out there that I've seen. Maybe someday the math will get better, but this is what we're dealing with now. Hopefully you learned something today. If not, I hope I opened up your eyes to potential problems. Other than that, I think I'm done. If you guys have any questions, you can post them in the question panel. I'll try to answer them. If not, have a good afternoon. This pretty much ends our presentation. Again, I hope you learned something throughout today. I hope if you get into 4-axis machining, you don't make some of the common mistakes. You know, doing these webinars, in my opinion, saves me a lot of support calls. Again, we can answer this stuff over support, but 9 times out of 10, just getting you guys aware of the way softwares think will make you better programmers. All right, I don't see any questions coming in. If you have questions in the future, just send them to your sales rep and they'll get them to one of the tech guys. We'll get answers for you. Anyway, have a good afternoon.